Now, we start a new topic called polya theory. Let us start with one of the question that we have visited many times so far in this course. That is, suppose I give you this 5 squares in a row, and I give you n different colors, and I ask you to color these squares using your choice of colors. Right? So you can choose for each cell, you can decide which color that you want to use, and then you have to color. Now, the first question that rises in combinatorics is how many different ways I can do this coloring, right? So how many different ways are there to color these 5 squares given n colors? Of course, the answer is very easy, right? For every square, we know that there are n choices for the colors, right? And I can, I am free to choose whichever color that I want. So I have n choices for each of the 5 boxes. So n raised to 5 colorings in total, right? So I get n raised to 5 distinct colorings of these squares. Now we can add some restrictions. For example, I say that, okay, we allow rotation of this figure by 180 degrees, right? I can just, rotate the entire thing by 180 degree. And then I say that if I can get one coloring, right, a fixed coloring of this strip by rotating another coloring, right? Then I will say, I consider them to be equivalent, right? I don't distinguish between them. So if under rotation I say that, okay, the coloring that is given to this, right, is the same, then I can say that the colorings are equivalent, right? For example, a coloring like this, if I rotate, I will get the same coloring, right? Now, then we can ask like how many different colorings are there now, right? How many inequivalent colorings are there? So, one can think of trying to solve this. We see that, okay, if I have n raised to 5 colorings in total, if I reflect them, I will get a set of colorings, and these colorings are equivalent, right, for corresponding, right? Like if I take any coloring, its reflection is also equivalent. So maybe I can try to divide by 2, but then there is a problem. If I divide, all the colorings by 2, will it work? Well, the problem is that like some colorings might be counted twice for this thing, right? For example, I might have a coloring where the reflection also gives the same coloring, right? So in that case, what happens? For example, let us say that I have this strip, and I color the first one with color A, second with B, third with C. Then I color the fourth with B, and the final one with A again. Now, if I reflect this, there is no difference. I get the same coloring, right, of the squares. And therefore, when I divide by 2, I am actually undercounting, right? So I need to take care of this. So I want to make sure that I don't overlook these kind of colorings. So what I do is that I just observe that the only type of colorings which which remains the same under the reflection are are precisely or rotation by 180, right? Rotation by 180 are precisely the colorings where some three colors are used in the first three boxes, and then the color of the second cell is used on the fourth, and the color of the first cell is used on the fifth. So any coloring like this, if I rotate, I will get the same coloring, right? Precisely the same. So therefore, such colorings I want to treat separately. So out of the total n raised to 5 colorings, right? This n cube colorings, because the first three cells I can choose any of the n colors, but then there is no choice because I just use the colors that I already have on the remaining cells. Okay? So out of this n raised to 5 minus n raised to 3 colorings, each of them under the rotation will give a different coloring, but they are equivalent, so therefore I can divide by 2. But on the other hand, I have this n cube colorings which are the same under the rotation also, so I have to add that. So this will be n raised to 5 plus n raised to 3 by 2. So we get this to be the number of inequivalent colorings, right? The distinct colorings where two colorings are same under rotation by 180 degree. Now, let us try to see how much more we can go in this direction, right? So the idea of Polya theory is to somehow generalize this. So what is the kind of thing that we can use to generalize something like this? So one thing that we observe, if you think about this, is this rotation that we are talking about, for example, is a kind of symmetry, or in fact it is a type of permutation of the elements of the set, right? So basically I'm permuting. I can think of this rotation as permuting the cells of this of the set of squares, right? So or the squares, individual squares. For example, I can say that this rotation is basically like I am permuting this square, right, going here, and this square going here. Similarly, this one going here and this one going here, and this square is mapped to itself. So such permutations, right, will give you the effect of rotation. And of course, the identity permutation will keep the same coloring. So if you want to think of this, you can think of this as basically these two permutations, identity and the permutation that maps 1 to 5 and 5 to 1, right? Then 2 to 4 and 4 to 2, and 3 to itself, right? The squares to itself as representing the rotation. And then you see that, okay, these two basically form a two element group, and it is going to be a subgroup of the symmetric group of all the permutations of the squares, things like that. So before going further with this, let me just recall what is this group and all we are talking about. It's a very quick review because I expect all of you to know group theory. So what is a group? Group is basically a set, right? Let's say G together with a binary operation such that this binary operation, under the binary operation, the set is closed. That if I add elements of the set, I will get still another element of the set. So it is closed under this binary operation. Now, then we have some additional properties, right? The group properties which are, for example, associativity, right, of the addition, right? Then existence of identity, identity element. Then existence of inverse element. Right? So these are the properties that we want, for a group to have, right? So we have such structures which we call groups. Now, example of a group, for example, is the set of all integers under addition. Now, if groups have subgroups, what is a subgroup? Subgroup of a group is basically a subset of the set G, and such that X plus, right, is a group by itself, a group. So if this is true for some subset, then it's called a subgroup. Okay, so we follow the same binary operation, the same rules, and this subset together with the binary operation is a group by itself. Then it's a subgroup of the group. Then associated concept is what is that? Is that of coset, right? Cosets, with respect to a subgroup, I can say that G is an element of G and H is a subgroup. Then elements GH are the left cosets. And similarly, you can define right cosets. And cosets partition the group. Right? So this is something that you can take it as a homework and prove if you have not done it before. So the cosets basically form a partition of the group. Now, and with respect to which subgroup you are looking at, you will see that the cosets have the same cardinality, and then it follows that the order of the subgroup, so the number of elements in subgroup, divides the order of the group, and things like that. So these results are all very standard in the in any mention of group theory. Okay, so now these things that you should know. Then another related concept is the action of a group on a set. Okay, so group acting on sets. So let's say that X is a set, right? Let's say that n element set, right? Okay, X is an n element set, and G is a group. Okay. Now we say that the group G acts on the set X. G acts on the set X if for every element of the group, if for every element, let's say, of the group G, we can we can associate a permutation. Okay? We can associate a permutation, and we will overload the symbol by saying that pi is also a permutation. Okay? So we will use the same thing, permutation of X, right? So permutation of the elements of X, such that for every element X in X, and two elements, let's say pi and sigma in G, we have pi of sigma of X equal to pi sigma of X. Okay, so pi sigma is basically the the operation under the group, right? So it's a binary operation in the group. So pi sigma I get, and then pi sigma is an element of the group. So therefore it has a corresponding associated permutation, right? Every element is associated permutation. So pi sigma is now an element which is also representing some permutation, right? So pi of sigma of x is equal to pi sigma of x. So if this is true for every x and every pi and sigma, then we say that the group G acts on x. Okay. Now, if you think about this, maybe you should try to give an argument why. The action of the group G is the same as a homomorphism. Okay, so action of the group G on the set X is equivalent to saying that there is a homomorphism say homomorphism, let's say 5, which maps from G to the symmetric group Sx. Okay. So Sx is the set of all permutations of X. Okay, so this is the symmetric group Sx. Now, this is something that you can work out the details and make sure that you understand what is a group, what's a coset, what is action of a group on sets and things like that. So these things you should be clear. Okay. So once this is clear, we can proceed. Now, so let us try to look these things in a more general way. So let us start with a set X, which is a finite set. Okay. Now we consider a group G as a subgroup of Sx, which is the symmetric group. Now this is this group is basically a group of symmetries of X, right? Because permutations can basically as a group can represent symmetries, and that is precisely the reason we call the group of permutations as the symmetric group itself. Now we have this group of symmetries. We have this group of symmetries, and in fact, see, when we are talking about the definition, when we are uh, defining the groups acting on sets, we are saying that we are basically associating permutations with this. But now one can see that whichever group that you find, you start with, you can associate associate permutations. Then that permutations form a subgroup of a symmetric group, and then you can as well start with the symmetric group as your group that you are looking at. Now, suppose so you have the finite set X, you have a group G, and then consider a set of colors, okay, C, which could be an infinite set of colors. Okay, so C could be finite or infinite, and elements of C are called colors. And a coloring of the set X is basically a function from X to C. Right? So you're basically associating colors with elements. Right? So we have now a coloring of an arbitrary finite set X. Then we can we can of course ask several questions like what are the number of colorings. Then we can ask like if under the action of this symmetry, a symmetric group G, can you say how many inequivalent colorings are there? So this is basically a generalization of what we are looking before. So let us look at an example. So X is the set of squares of a 2x2 chessboard or board, labeled as let's say, okay, I think I have. Mhm. 1, 2, 3, 4. Okay, so maybe I will redraw this. So I have these 4 squares, 1, 2, 3, 4, right? Now, let us say that C is this finite set R comma B comma Y. It's a set of colors, so red, blue, and yellow. Okay. The coloring of X is using the colors from C. Can be one of the examples is, for example, you give the first cell as R, second as blue, then the third as yellow, and the fourth as red, right? So RBYR, which means that F map from X to C is f of 1 is equal to R, f of 2 is equal to B, f of 3 is equal to Y, and f of 4 is equal to R, right? So we have a coloring of a finite set X. Right? Now, given this, we can ask some questions, and for that, let us define the following. So we define two colorings F and G, to be equivalent or G equivalent, and we denote it by F tilde G, right? So F tilde G says that F and G are equivalent. If we can find some permutation in G, because G is the symmetric group. So if we can find a permutation in G such that G of phi of X is equal to f of X for every X in X, right? So if I can do this, then we say that F and G are equivalent. So we can write, for example, G pi is equal to F, right? The composition of G and pi is basically the coloring, right? Now, so coloring F, right? So now prove that this relation that we defined, the equivalence relation, right? So G equivalent is an equivalence relation, right? I mean, so the reason we call this as F and G are equivalent is because this happens to be an equivalence relation, but you need to prove this. So it's quite easy. Just prove that tilde is an equivalence relation. Continuing our example, so we have the set X, which is the set of all set of these 4 squares, right? And C is the colors R, B, and Y. Now the symmetric group G, right? So we said that G is basically is a subgroup of the symmetric group on all these elements on X, Sx. And since our Sx in this case is basically S of 1, 2, 3, 4, right? There are four elements at X. So we can look at any of the subgroups of this S4. So, for example, maybe the symmetric group is precisely the identity permutation. The identity by itself forms a group, so therefore it's a subgroup of the symmetric group Sx, right? So G1, let me say, is the group with only one element, which is identity permutation. So what is identity permutation? This 1 goes to itself, 2 goes to itself, right? 3 goes to itself, and 4 goes to itself. So all the elements goes to itself. Then G2, right? So is basically the vertical reflections. So if you look at the vertical reflection, what happens if I take a vertical mirror and then reflect on this? Then you will see that under the reflection, 1 will be going to 2, right? So we have this labeling, right? What is that? 1, 2, 3, 4, right? 1 will be going to 2, and 3 will be going to 4. So this is represented by this permutation, 1 going to 2 and 3 going to 4. Of course, the identity is always equivalent, right? The coloring is equivalent to itself. So therefore, identity is always there. So therefore, we have G2 is consisting of these two permutations, 1, 2, 3, and 4, right? And 1, 2, 3, 4, right? So these two permutations form another subgroup with just two elements. Then we can look at the reflection on the main diagonal, right? So, I mean, I can put a mirror on the diagonal and then try to find the reflection. So 1, 2, 3, 4 again is there. Now what happens under the reflection on the main diagonal? Of course, this cell will be preserved as it is, right? This cell will remain as it is, but this will go here and this will go here. So basically, this is represented by one going to itself, 4 going to itself, and 2 is going to 3 and 3 going to 2, right? So G3 is the reflection on the main diagonal. That is also a two element subgroup. Now you will see that as abstract groups, if you have studied group theory, you will see that abstract groups, G2 and G3, for example, right, are isomorphic. Okay? We have not defined isomorphism, but in any group theory course you will see. So they are isomorphic, but we will see that their actions are different, right? So as permutation groups, they are basically different objects. We will see this soon. Then we look at G4 as the group of rotations of X. So what is basically the rotations? Rotations are basically like, so this 1, 2, 3, 4 is there, right? I just rotate the entire figure, right, by 90 degrees. So these are the rotations. And what are the what are the elements of the permutation group which does this job, right? Of course, the identity is the rotation where we don't do anything, right? Then 1 going to 2, 2 going to 4, and 4 going to 3, and 3 going to 1. Okay. So 1 going to 2, 2 going to 4, 4 going to 3, and 3 going to 1. It's one rotation by 90 degrees. Right? Then if I have two rotations, then 1 will go to 4, right, after two rotations. And 2 will go to 3, right? And 3 will go to 2, and similarly 4 will go to 1, right? So I get this permutation. And similarly, if I rotate 3 times or rotate to the left, then I will get 1, 3, 4, 2. So 1 going to 3, 3 going to 4, 4 going to 2, and 2 going to 1. So these are the rotations, and these form a subgroup, which is called G4 in our case. Then we can talk about G5, which is the dihedral group of all rotations and reflections. Okay? So we already saw that the rotation has all these 4 elements. Then we have the reflections, right? Reflections on the main diagonal and the horizontal, vertical, etc. So these forms altogether 8 elements. So what are the elements? So the reflections 1 going to 2, 3 going to 4, right? So 1 going to 2 and 3 going to 4. So that is the reflection, vertical reflection. Then 1 going to 3 and 2 going to 4, which is the horizontal reflection. Then 1 and 4 remains, 2 and 3 are interchanged, which is the reflection on the main diagonal. And then 2 and 3 are remaining itself, and 1 is going to 4, which is a reflection on this diagonal, right? Diagonal including 2 and 3. So this is the dihedral group, which consists of all rotations and reflections. Then finally, we can also look at the symmetric group of all permutations of X, G6. Okay, so Sx is S4 itself. Now, so if you look at all possible permutations, then we see that actually it loses the connection with the geometric representation of X as a as this 2 by 2 square, right? Because when we allow all possible permutations, right, then and they are all considered identical, then there is precisely nothing to differentiate, like whether there is this figure where is this figure or not, right? Whatever the shape of the figure, it's instead of 1 2 3 4 as a 2 by 2 square, you can have it 1 2 3 4 as a as a line, not line, I mean, as a sequence of four these things. Or put in another fashion, all of these are immaterial. What is the shape, it does not matter. So you will see that the when you take the full symmetric group, then the shape or geometric representation does not matter, so that we lose the meaning. But of course, it's a valid permutation group. Then under all these six groups, we can talk about the inequivalent colorings of X, where we specify our set of colors. Let's say we are saying that we always use two red colors, right? Like two squares will be colored with red always, and one will be colored with blue, and one will be colored with yellow, for example, right? So if you specify the number of times each color appears, then we can talk about the action of the group.